Welcome all. This is a second session of the topic nonlinear dynamics and chaos. In the last session, we have discussed singular points and trajectories. Now we know how to plot the phase space of a differential equation and how to extract information from that phase space. We are also familiar with different kinds of singular points of the trajectories like center or vortex, saddle point, focus and node. We also discussed stable and unstable fixed points in the last session. In this session, we are going to discuss nonlinear oscillations with a special emphasis on two examples. One is a nonlinear simple pendulum and other is a hypothetical example. That two equations we will discuss here and how to extract information from phase space for a nonlinear oscillation. Here we are going to start with nonlinear oscillations. Now let us look the equation of a nonlinear oscillator in general form. The equation of a nonlinear oscillator in general form, we know it is x double dot plus some f of x. F of x will be a nonlinear function of x. F of x equal to 0. If f of x is linear, we can say that this is a linear oscillator. If f of x is a nonlinear function of x, then we can say that it's a nonlinear oscillator. Say for example, you can say this x double dot plus some constant k into x equal to 0. This is a linear oscillator, linear harmonic oscillator. And if you write this x double dot plus some k of x into x equal to 0, the second one is a non-linear oscillator. The first one is a linear oscillator because it's a linear function of x. Here the f of x is kx. In the second case, f of x is k of x into x. This k of x can be anything, any function of x. It can be sin x, cos x, log x, x square, x cube, whatever it is. Now, if f of x is a non-linear function, we call this as a non-linear oscillator. Now, we can represent the general form of a non-linear oscillator as x double dot plus f of x equal to 0. Let me call this as equation number 1. Equation number 1. Now we are going to do the phase space analysis that already we know. Let us put x dot equal to y. X dot equal to y. When x dot equal to y, x double dot equal to, we know that x double dot is y dot. If you substitute here, x double dot is y dot plus f of x equal to 0. This implies y dot equal to minus f of x. Y dot equal to minus f of x, that we can say. Y dot equal to minus f of x. Then we have dy by dx equal to, you have dy by dx equal to y dot divided by x dot. This is y dot is minus f of x. This procedure we already know, we have discussed in the last session. Minus f of x divided by y, and you can represent this as some q of xy divided by p of xy. Q of xy divided by p of xy, we can represent like this. Dy by dx equal to minus f of x divided by y, minus f of x divided by y. We can say that the singular points of the phase space are located at we know that it is at q of xy equal to 0 and p of xy equal to 0. These are the singular points. That is f of x equal to 0 and y equal to 0. F of x equal to 0 and y equal to 0. So the singular points of the integral curves are located at points where y equal to 0 and f of x equal to 0. We know this thing, the singular points are located at y equal to 0 and f of x equal to 0. Now just look equation 1 again. We have this equation x double dot plus f of x equal to 0. I'm going to multiply this equation with x dot. We have x double dot plus f of x dot equal to 0. But you know x dot equal to y and x double dot equal to y dot. Now we can write this as y dot y plus f of x dot equal to 0. Y dot y plus f of x dot equal to 0, or we can write this as y dy by dt plus f of x dx by dt equal to 0, or y dy plus f of x dx equal to 0. If we integrate this relation, y dy, the integral we know that y square by 2. We are going to integrate here, integrating y square by 2 plus integral from 0 to x f of x dx equal to a constant. Say that constant is e, equal to a constant e. So this integral, you just look, y square by 2 plus integral f of x dx equal to e. Actually this integral is the energy integral. Here this y square by 2, you can see the term y square by 2 is the kinetic energy, and integral f of x dx may be thought as the potential energy. We will say that E stands for the total energy. Here y square by 2 stands for kinetic energy and integral f of x dx stands for potential energy. Now we can write this expression as y square by 2 plus v of x equal to E, or we can rearrange y square by 2 plus v of x equal to E, or y equal to, what we can write, you can see y square equal to some E minus v of x, and E minus v of x in E minus v of x. This is y square by 2, and you get y equal to 2 E minus v of x square root of 2 into E minus v of x. This equation represents the phase trajectories of the above differential equation. We have the differential equation 1, y equal to, this relation represents the phase trajectories. Using this relation we can plot phase space, and we will show how it can be achieved by using an example. First of all, we will use a hypothetical example, and after that we will come to a real example, that is simple pendulum. Now let us look at an example. F of x equal to x into x plus a. To remember our differential equation, x double dot plus f of x equal to 0. This is our differential equation. X double dot plus f of x equal to 0 is our differential equation. In the place of f of x, we are taking a non-linear function x into x plus a, or x square plus ax. We are taking this function x square plus xa. Now let us calculate the singular point. We know that the singular points are located at y equal to 0 and f of x equal to 0. Singular points are located at y equal to 0 and f of x equal to 0. So here f of x is x into x plus a. F of x is x into x plus a. X into x plus a equal to 0. X into x plus a equal to 0 means x equal to 0 and x equal to a. X equal to 0 and x equal to a. That means this function has two singular points, or this differential equation has two singular points. One singular point is at x equal to 0 and the second singular point is at x equal to a. Second singular point is at x equal to a. Now let us calculate df by dx. We just calculate df by dx. Df by dx. We know that v of x is taken as integral f dx, so that f will be dv by dx and df by dx will be d square v by dx square. That is the second derivative of v, and we can calculate the maximum and minimum of v from this relation. This df by dx, you just look, df by dx is 2x plus a. 2x plus a. Now at x equal to 0, so you substitute here x equal to 0, you have df by dx equal to plus a. Plus a. We know that df by dx is nothing but d square v by dx square. D square v by dx square is positive and it corresponds to a minimum of v. It's a minimum of v. Now at x equal to minus a, this df by dx equal to, you substitute minus a here, 2 into minus a plus a, this is minus a. So the second derivative, that is d square v by dx square, is negative, so it corresponds to a maximum of v. Maximum of v. It corresponds to a maximum of v. Now we can plot the functions and we can obtain the phase space trajectories. We just see how to obtain the phase space trajectory here. You just see these three graphs. The first one is f of x versus, here it is f of x versus x. F of x versus x. This is the graph. You can see this graph. This is the graph. F of x versus x. F of x versus x graph is this one. The first one. The second graph is the graph obtained from first one, that is v versus, v is nothing but df by dx, v versus x graph. V versus x graph. V versus x graph. You can see this v versus x graph, its trajectory. Just see this. This is v versus x graph. This graph is actually v versus x graph. V versus x graph. And you can see two singular points here. This is the first one. This is at x equal to 0. X equal to 0. And this is the second one. This is x equal to minus a. X equal to minus a. X equal to minus a. We know that at x equal to 0, v is minimum. And you just refer here at x equal to 0, minimum of v. And x equal to minus a, v is maximum. You can see that at x equal to minus a, v is maximum. We have plotted that function df by dx. And from this potential function, we can extract the phase space trajectories, and we can extract it numerically. I already stated that we can extract phase space from potential functions numerically by solving these two consecutive relations. You just look this x equal to 0. This x equal to 0. Actually, x equal to 0 is a center or vortex. And in the third graph, you can see the phase space trajectory. Here, this is x and y versus x graph. This is a phase space trajectory. X, y graph is a phase space trajectory. Now you can see the graphs. Just see the ellipse here. One phase space graph. You just look this graph. This is an ellipse. It corresponds to a particular total energy value. This is a potential function. So that depends on the total energy value of the system. It can have various type of motions. You just see here. You can see this line. This is the energy value. This value is E1. This energy value is E1. You can see here. This energy value is E1 here. This energy value is E1. For energy value E1, the motion is bound about x equal to 0, and you can see that the phase space is almost an ellipse, and actually speaking, for very small values of x, it will be exactly ellipse, otherwise it will be a closed curve. We can say that it's a closed curve. So this x equal to 0 corresponds to a vortex or center, and for value of energy E1, the phase space trajectory is a closed curve as shown. And you just see for energy value E2, just see this energy value E2. This is energy value E2. E2. You can see the phase space trajectory like this. You can see the phase space trajectory. This is for energy value E2. Energy value E2. You can see these two kinds of trajectories, one for energy value E1 and other for energy value E2. This closed trajectory indicates periodic motion or oscillations. It indicates oscillations. You can see various kinds of trajectories. What happens to that phase space trajectory as the value of x has increased. You can see the trajectories here. These are the phase space plots for this particular potential. Here you can see that this trajectory becomes hyperbolic. Here, hyperbolic, and also for high energy. You just see this motion for energy greater than E2. This is a phase space trajectory. If the energy is greater than E2, what this is a phase space trajectory. You can see the phase space trajectory. Okay. You just see if energy is less than E2, what happens is it will oscillate in this potential, and for very small values of energy it becomes simple harmonic oscillations. And if the energy is greater than E2, what happens is it may overcome this potential and goes to the unstable situation, unstable case. So again, if energy you can see if it starts from this region, So the trajectory is hyperbolic, you can see this. So corresponding to this potential function, we can plot the phase space trajectories. So here you can see this point S is a saddle point. S corresponds to a saddle point, and S means this S, that's x equal to minus a corresponds to a saddle point, and x equal to 0 corresponds to a vortex. So now let's go to a second example, simple pendulum. For simple pendulum oscillations, you can see the simple pendulum here. Here this is simple pendulum, mass m, and say length of pendulum is L. You can see its oscillation. You can see its oscillation. This is the equilibrium point. So it is oscillating like this. For an angular amplitude theta, we know its potential energy is V equal to mgl into 1 minus cos theta. We are familiar with this. Potential energy V is mgl into 1 minus cos theta. 1 minus cos theta we can write 2 sin square theta by 2. We can write this as 2 mgl sin square theta by 2. Let me take theta equal to x, and all parameters this 2 mgl constant as 1. Now we can write this as v equal to some sin square x by 2. This is a sin square function. The sin square x by 2, sin square x by 2, and we know y equal to root of 2 into e minus v of x, root of 2 into e minus some sin square x by 2, some sin square x by 2. This is y. This equation determines. Now to plot the phase space trajectory, what we have to do is we have to numerically simulate this equation. This is an equation which connects y and x. You can see sin square x by 2 here. E is a constant. For a given value of e, you can plot xy graphs. Manually, it's not easy. You can plot the graph. You just listen how to plot the phase space trajectory. We have this relation y is equal to root of 2 into e minus v of x. This is a relation connecting x and y. You can numerically simulate this equation to obtain the phase space trajectory. In the case of simple pendulum, you have this relation y equal to root of 2 into e minus sin square x by 2. For the sake of simplicity, I have taken all other constant as 1. All other constant as 1. Now 2 into e minus sin square x by 2. Now if you add constants, what would be here is you would get the relation like this. It would be like this, root of 2 divided by ml square e minus 2 mgl sin square x by 2. If we keep the constant, it will be like this. If we keep this constant, e minus 2 mgl sin square x by 2 will be the relation. That is, we have taken this 2 mgl as 1 here, and theta equal to x, and after that we have obtained like the sin square x by 2, and we just omitted the dimensions and constants. So this is e minus sin square x by 2. If you actually solve it, you can try that also. If you keep the constant, you can see that this relation will be y equal to some root of 2 by ml square e minus 2 mgl sin square x by 2. Now let us see the phase trajectory. can see the phase space diagram here. Phase space diagram. The first diagram is the potential V versus, this is V versus X graph. V versus X graph. We know that V of X equal to some, V of X is a function of some sine square X by 2. So that this graph is a sine square graph. You can see this graph. It's a sine square graph. Corresponds to sine square function. This is a graph. From this graph we can obtain phase space diagram by numerical analysis. You just see what all things are here. You can see for energy value E1, you can see the value of energy E1 here. Just see this energy value E1, this is the corresponding energy value E1. For energy value E1, you can see various types of motions. You can see ellipse around point O, and also find its singular points. You can see it can have various singular points at 0, pi, 2 pi, etc. It have infinite number of singular points also. At x equal to 0 there is a singular point, pi also there is a singular point, 2 pi also singular point, and you can see the phase space diagrams. This one is an ellipse for small angular amplitudes. It's an ellipse, and that we are familiar. For small angular amplitudes, the oscillation of simple pendulum is linear harmonic. Then also if you have another energy here, say some E dash, energy E dash, you can see it will be another ellipse around O. This is the phase space diagram corresponding to energy E dash. You can see this E2. This E2, energy value is E2. For E2 you can see this trajectory, and for energy greater than E2 you can see this energy diagram for E3. This energy is E3. You just see the phase space diagram. This is the phase space diagram for E3, energy E3, and it indicates revolution. It is not oscillation, it indicates revolution. So for energy less than E2, the motion is oscillatory, and for energies greater than E2, the motion is circular motion. Now at a particular value of energy E2, this is a phase space. You can see here this point P corresponds to a saddle point, P corresponds to a saddle point, O corresponds to a center or vortex, and this trajectory, actually this trajectory separates two kinds of motion. One is oscillatory and other is circular. So we call this as the separatrix. We call this as a separatrix. Now you just look E less than 2 mgl. Let us look this equation once again. E minus 2 mgl into, this is y value, y equal to 2 by ml square, E minus 2 mgl sine square x by 2. So for different values of E, for E less than 2 mgl, it represents oscillatory motion. This is the result we are getting from the phase space. For E less than 2 mgl represents oscillatory motion. Phase trajectories are closed loops around O, and O is a vortex or center, vortex or center. At the same time, you can take this as E less than 1 also. In place of 2 mgl, you can take, if you are using that dimensionless equation, you can take E less than 1, E greater than 1, and E equal to 1 at the same time. If you use dimensions, that's, we have two relations here. If you are using this one, you can simply use E greater than 1, less than 1, and so on. Here, if you are using the second equation, let us use E greater than 2 mgl and less than 2 mgl, greater than, less than, and equal to, greater than, less than, and equal to. In these two ways we can use either we can use 2 mgl, so or we can use one dimensionless. So if E greater than 2 mgl, we can say a system revolves around its point of support continuously. The phase space trajectory is a curve that continues with the x, that we also know. And at E equal to 2 mgl, that is phase space trajectory in this case is called the separatrix. And see here, because it separates the motion of one type from one type, means one is oscillatory and the second is circular motion. It separates these two kinds of motions. These two motions are entirely different, and the point P is a saddle point. P is a saddle point. It's an unstable fixed point. It's a saddle point. P is a saddle point. Now let me conclude this session. In this session, we discussed non-linear oscillations with two examples. In the first example, we have taken the non-linear function f of x equal to x into x plus a. And in second example, simple pendulum was taken. We know the potential function of simple pendulum is 1 minus cos x or sine square x by 2. And we simulated phase space diagram from these potential functions. And also, we discussed how to plot phase space from a potential function. We have taken the differential equation, general form of differential equation of nonlinear oscillations. Using phase space dynamics, it was analyzed and finally obtained a relation y equal to root of 2 into e minus v of x. If potential function, that is v of x, is known, the relation y equal to root of 2 into e minus v of x relates x and y, and from that relation it is not easy to plot the phase space manually. We can use some computer programs or we can use some numerical simulations for any potential functions, any kind of potential functions. We can obtain the phase space diagram, and from the phase space diagram we can extract the necessary informations about the system. This is about nonlinear systems, and in next session we will discuss the different kind of attractors and the different versions of the nonlinear oscillations. So thank you all for hearing this session.